Section 5.6 is about radical expressions, what we do with different expressions that involve radicals and how we deal with them. First, one of our key concepts is the product property. What do you do when you multiply radicals that have the same index? Well, if the n is even, and then a and b are both positive, then you can multiply them together. If n is odd, you don't have to worry about it being positive. You can just multiply them together. And you can also break them apart. That's the other thing that you can do. Take an example down here, square root of all of this stuff. This is actually the square root of 16. And then we're going to break it apart into 16 times the square root of p to the 8th and times the square root of q to the 7th. Now let's do each one of those individually. You may know the square root of 16 is 4, but why is it 4? Well, because 4 squared is 16, and the square and the square root will cancel, leaving just a 4. Same idea here, because it's a square root, I'd like to write p so that it had a something squared. Well, if I read it as p to the 4th squared, I can then take its square root and cancel the square and the square root, leaving me at p to the 4th. Q to the 7th has an odd exponent. The way you deal with that is you take one of them out. So I have square root of q to the 6th, and then this extra square root of q on the back. Now this one I want to write as q to the 3rd squared, again, so the square and the square root will cancel, leaving me a q to the 3rd. And there's nothing that really I can do with the square root of q. It's got to be there at the end. My final answer will be 4 p to the 4th q cubed times the square root of q. Now, one thing to look out for, did we have any even exponents that ended up being odd? And the answer is no. This p to the 8th became p to the 4th, so we don't need any absolute values. There's also a quotient property of radicals that says if you take the nth root of a quotient, you can break that up, take the nth root of the numerator and the nth root of the denominator. There's an example here for you to look at. Finally, simplifying radical expressions involves all these steps. You must have an index that's as small as possible. The radicand must have no factors that are of the nth power. There can be no fractions under the radicand. There can be no fractions in the radicand, and there can be no radicals in the denominator. If you've taken care of all those things, then you've simplified a rational expression. Now, eliminating a radical in the denominator is something that we're about to do. That's called rationalizing the denominator. Here's some examples of that. Right now I have the square root of x to the 4th over the square root of y to the 5th. I'm going to break this up and show you a way I can simplify it. Well, the square root of x to the 4th, how can I get rid of a square root? The answer is with something squared. So I'm going to rewrite this as x squared squared, so that I can cancel the square root and the first square, leaving me with just an x to the 2nd on top. Well, that's nice. That's one way to get rid of the radical. A y to the 5th is a little more complicated. I make it y to the 4th times the square root of y. Now, how will square root of y to the 4th simplify? Well, the same exact way it's simplified up here. It's going to become a y squared, and then I still have that square root of y hanging around on the bottom. So I'm going to rewrite. So now I have to rationalize the denominator. I can't have a square root in the denominator, so I have to get rid of that. The question is, what can I multiply the square root of y by to get rid of the square root? And the answer is you multiply by itself. Let's see how that works. On the top I'll have x squared times the square root of y. There's nothing I can do with that. But on the bottom, I will have y squared, and then I'll have the square root of y squared. Because I can multiply y times y, I get y squared. Now the square and the square root will cancel, leaving just a y, and now I can multiply the two y's on the bottom. Second example has a 5th root. So the 5th root of 5, that's nothing special, just leave it like that. And then the 5th root of 4a. Now I have to get rid of a 5th root, so the question is, what can I multiply a 4 by and an a by to get something that's of the 5th power? Because if I can find something that I can write as a 5th power, I can cancel the 5th root. I know that 32 is 2 to the 5th power. I'm writing this down here. I know 32 is 2 to the 5th power. So if I can turn this 4 into a 32, I'd like to do that. And I do that by multiplying by 8. So I'm going to multiply by the 5th root of 8. And then also I have an a. If this was an a to the 5th, it would cancel. So I'm going to multiply by a to the 4th. And I'll show you why here in just a second as I write the rest of this down. Because you have to multiply by the same thing over itself. Now, I can multiply them together because they're both 5th roots. So on the top, I'm going to have the 5th root of 40 a to the 4th. Now, there's nothing up there that simplifies, so we have to leave that alone. But on the bottom, I'm going to have the 5th root of 32, which is good, and a to the 5th. Let's see how that simplifies. I can break the denominator up into the 5th root of 32 and the 5th root of a to the 5th. Now, we know the 5th root of 32 is just a 2, and we know the 5th root of a to the 5th is just an a. So we've actually engineered all these 5th roots and these 5th powers so that they would cancel. And now I have a denominator that has no square roots. The numerator can't be simplified, so I'm done. Here's some more radical expressions to simplify. I'm multiplying. I can multiply the whole number portion, so I can do the 6 times 3 and get an 18 on the outside. And then I can multiply the cube root portion. So it's okay for me to multiply the cube root of whatever's under there times the cube root of whatever's under there. So I'm actually going to do 9n squared times 24n, and all of that's going to be under the cube root. 24 times 9 is 216, and n squared times n is n cubed. Now I want to see if this can simplify at all. So this is really the cube root of 216 and the cube root of n to the 3rd, or n cubed. Well, if you plug that into a calculator, you find out that the cube root of 216 is actually a 6. So this becomes 18 times 6. And the cube root of n cubed, you know you can cancel those, leaving just an n. So now all I have to do is multiply 18 times 6, and I get 108 n. Now when you add radicals, they're not added the same way they're multiplied. They're added like you add monomials. When radicals have the same indices, or indexes if you want, and the radicands are the same, they're called like radicals, or like radical expressions. Let me give you some examples. You know from algebra that you can add 3x squared plus 1x squared and get 4x squared. Okay, those are called like terms, and that's legal to add those together. It's the same way with radicals. If I have the square root of 4 and I have the square root of 3, I can't add those together and get something like a square root of 7. I can't put them together because they don't have the same index and they don't have the same radicand. Likewise, square root of 3 plus the cube root of 3. I can't add those together either because they don't have the same index. So those cannot be added. There's really nothing you can do to that. Now if I give it the same index, can I add those together? No, I can't because they don't have the same radicand. They both should have 4th root of 5x. So I can't put those together either. But something like this. Now here's an example where I can add these two together because they both have the 4th root and they both are of 3a. So this is 2 4th roots of 3a plus 5 4th roots of 3a equals 7 4th roots of 3a. Here we're asked to simplify. In the number 12, I know that there's a perfect square of a root 4. And the reason I want that is because then I'm going to have 2 times 2 times root 3, which is 4 root 3. That's simplifying this radical. How about the square root of 27? Is there a perfect square in 27? The answer is yes. 9 times 3, so this becomes 3 times 3 times root 3, which is minus 9 root 3. How about 48? Can you think of a perfect square? Can you think of a perfect square that's in 48? 16, so the square root of 16 times the square root of 3. Square root of 16 is just 4, so that's a 2 times 4 times root 3, which is 8 root 3. So by simplifying each one of these, I end up with 3 like radicals, because I can add root 3, and root 3. I can add or subtract those. So 4 minus 9 is negative 5. Negative 5 plus 8 is 3 square root of 3. Simplifying some expressions that are being multiplied. In this case, you would FOIL or distribute. So 3 root 5 times 2 is 6 root 5. 3 root 5 times root 3 is plus 3 root 15. Negative 2 root 3 times 2 is negative 4 root 3. And negative 2 times square root of 3 is, negative 2 root 3 times the square root of 3 is negative 2 square root of 9. So we'll simplify square root of 5. There's nothing I can do with that. 3 root 15, there's no perfect squares in 15, so that's going to stay there. I can't simplify 4 root 3, but the square root of 9 is just 3. And that 3 times the 2 that's already there will give me a minus 6. So that one's done. You might want to pause this one and try it on your own. Here, if you distribute this one out, you get what I wrote over here by distributing, and you'll notice the 2 middle terms will cancel because one's positive and one's negative. Square root of 9 is just a 3, and 25 times 3 is 75. 75 minus 36 is 39. One thing you also may have noticed is that these are the same except the plus and minus sign. So you may have remembered the difference of squares and realized that you could have squared the first term, squared the last term, and put a minus sign in the middle, and you would have got the same answer. Last example, we have to rationalize this denominator, but we can't just multiply by root 3 over root 3 because that will get rid of the square root of 3 here, but when you distribute, it'll create another square root, so we're going to have to use an idea called conjugates. When you have an expression on the bottom, you're going to use conjugates, and conjugates are the idea of difference of squares. When you have two binomials that are the same with a plus and a minus, you can square the first, square the last, and put a minus sign in the middle. Okay, this is the idea of using conjugates that we're going to incorporate here. So to get rid of a 5 plus root 3, I'm going to use 5 minus root 3. Top, we're going to have to distribute or FOIL. 1 times 5 will be 5. 1 times negative root 3. Negative root 3 times 5 is negative 5 root 3. And the negative root 3 times negative root 3 is a positive square root of 9. Let me just simplify that real quick. This is a 5, and this is going to simplify to be a 3. So you're going to end up with 5 plus 3, which is 8. And this is negative 1 root 3 minus 5 root 3 is negative 6 root 3. So there's my numerator. Denominator, because you have a plus and a minus with everything else being the same, going with the conjugate pattern, I take the first term and square it. I take the last term, square it, and I put a minus sign in the middle. Well, 5 squared is 25, and root 3 squared is just a 3. And 25 minus 3 is 22. So this would be my final answer, but there's still a little simplification that has to be done. If you look at the top, 8 minus 6 root 3, I can pull a 2 factor out of the top, leaving a 4 minus 3 root 3 over 22, and then I can cancel the 2 and the 22, leaving an 11 behind. So my final answer, 4 minus 3 root 3 all over 11.